You know, it's funny how we think about keeping our houses warm. I mean, we spend thousands on these high-tech, ultra-efficient HVAC systems,
Yeah,
right?
absolutely. Smart thermostats, the works.
Exactly. Smart thermostats that learn your daily schedule. And then, after all that, we essentially throw a winter hat on the house that's, well, entirely made of Swiss cheese.
Yeah, and the craziest part is that most people don't even realize the hat has holes in it.
Right.
They look at their energy bills, they feel a cold draft, and they just assume the furnace is failing. When in reality, the home's thermal envelope, specifically the ceiling, is just leaking like a sieve.
So today, we are fixing that hat. Welcome to a brand new deep dive, everyone. Our mission today is to give you, the homeowner, the ultimate guide to insulating your ceiling.
It's a big topic.
It really is. We are pulling together a massive stack of sources today, everything from Energy Star guides and Building America Solution Center manuals to some really dense building science research and cutting-edge state energy codes.
Yeah, we really dug into the weeds for this one.
We did. Because our goal is to figure out the right materials, the correct methods, and honestly, the massive, expensive gotchas that you need to avoid.
Because the ceiling really is ground zero for home efficiency. It's not just about warmth. It manages a highly delicate ecosystem of airflow, moisture, and thermal resistance.
Wow, an ecosystem.
Yeah, it really is. If you treat it like a simple weekend DIY project without understanding the physics, you might actually create worse problems than you started with.
Okay, let's unpack this, because I've got to admit, I always assumed insulating a ceiling just meant driving to the hardware store, buying those massive rolls of itchy pink fiberglass, and just unrolling them between the joists.
And dusting off your hands, right?
Right, job done. But according to our sources, doing that first is apparently the single most common mistake people make.
It's a huge mistake.
So we have to address the invisible enemy before we lay down a single inch of insulation, and that is air leaks.
Yes, we have to separate two completely different jobs here.
Okay, what are they?
Well, air sealing stops convective heat loss. That's the physical movement of air from one space to another. While insulation slows conductive and radiant heat transfer. Basically, heat moving through a solid material.
Okay, the sources gave a really great analogy for this that made it click for me. Think of it like this. Throwing insulation into a leaky, unsealed attic is like walking outside in January wearing a brand new, super thick down jacket.
But leaving the zipper completely wide open.
Exactly. The jacket has plenty of insulation, but the cold wind just bypasses it entirely.
Right, because the thermal boundary and the air barrier have to be in perfect alignment. If they aren't, the material just fails.
Hang on, I need to push back on this a little because I have a hard time visualizing it.
Sure.
If I put, say, 2 solid feet of dense fiberglass up there in the attic, I mean, it looks like a solid wall. How on earth does a draft just ignore 2 feet of physical material? Doesn't the sheer mass of it block the wind?
You'd think so, but no. Traditional insulation like fiberglass doesn't work by being a solid wall.
It doesn't.
No, it actually works by trapping microscopic pockets of still air between its glass fibers. It's those still air pockets that resist the flow of heat. But the material itself is highly porous.
Oh, I see.
Yeah, so if there's a pressure difference driving air through the ceiling, that moving air simply weaves right through the fibers, displacing the still air. The heat is literally carried away.
That's wild.
And that pressure difference is relentless because of something called the stack effect.
The stack effect. Yes, this concept was fascinating in the reading. It basically means your house acts just like a giant chimney.
That is exactly what it is. Warm air is less dense than cold air. The molecules are moving faster and spreading out, so the warm air naturally rises.
Right, heat rises.
Exactly. So in the dead of winter, all that expensive heat from your furnace goes straight up to the ceiling. Now imagine that ceiling plane isn't a continuous barrier, but a piece of Swiss cheese.
Like we were saying earlier.
Right. You've got holes for recessed lights, plumbing stacks, electrical wires, the attic hatch.
And nature abhors a vacuum. As that warm air punches through those ceiling holes and escapes into the unconditioned attic, it depressurizes the lower levels of the house.
Yep. The house basically starts acting like a giant vacuum cleaner.
Ooh.
To replace the air escaping out the top, it sucks freezing cold outdoor air in through the basement, crawl spaces, and tiny gaps around your doors.
So you are literally paying to heat the outdoors while actively pulling freezing drafts right across your living room floor.
It's the worst case scenario.
So the actionable takeaway here for you listening is that the ceiling plane has to be sealed completely. You have to go up into the attic, Pull back the old insulation, find all those penetrations, and plug them with expanding foam and caulk. You have to zip up the jacket first.
Absolutely. And, building codes are really catching on to this and getting incredibly strict about air sealing.
Oh yeah, they mentioned blower door tests.
Right. Assessors use a blower door test to measure a home's air tightness. They set up a massive fan in your front door, depressurize the house, and calculate the air changes per hour, or ACH.
Let's pause on that because the metrics can get a little confusing. In regions with aggressive codes, like Connecticut, they mandate an ACH of 3 or less at 50 pascals of pressure.
Which is very tight.
But what does 50 pascals actually mean in plain English? Is that like a gentle breeze or a hurricane?
Well, 50 pascals is roughly equivalent to a 20-mile-per-hour wind blowing against all sides of your house simultaneously.
Oh, wow. All sides at once.
Yeah, it's a significant constant pressure. Achieving an ACH of 3 at that pressure means your house is incredibly tight.
And what about older homes?
Unsealed older homes might measure an ACH of 10 or 15, meaning all the conditioned air in the house leaks out and is replaced by outdoor air 15 times every hour under those conditions.
15 times? That's insane.
Yeah, so sealing those hidden gaps in the attic floor is really the only way to get those numbers down.
Okay, so the jacket is zipped, the ceiling is airtight. If keeping the wind out is step 1, step 2 is figuring out what actually goes inside that airtight cavity to trap the heat. And according to the sources, just grabbing whatever's cheapest at the hardware store might be a recipe for disaster. Because it turns out the architecture of your roof completely dictates your strategy.
It really does. You basically have 2 diverging paths here depending on your home's design. You either have a vented attic or an unvented cathedral-style ceiling.
Let's start with the vented attic, since that's what most people picture.
Right. You have a flat ceiling over your living space and a big open triangle of roof above it. In this setup, the insulation sits completely flat on the attic floor. The attic itself is unconditioned space. It's effectively the outdoors.
And this brings up a detail that seemed completely counterintuitive to me when I was reading.
Oh, the baffles.
Yes, the baffles. If you have a vented attic, you have to install these things called rigid ventilation baffles and wind dams in the rafter bays. So air comes in at the soffit vents under the edge of the roof, travels up these baffles and out the ridge vent at the very top. But wait, if the whole point is to keep the cold out, why on earth are we intentionally leaving a 2-inch channel for freezing outside air to blow right into the attic? Doesn't that defeat the purpose?
I know, it feels like a total paradox. But that vented cold air isn't there to cool the house. It's there to manage the roof deck temperature and moisture.
Okay, how so?
Think about what happens after a snowstorm. If you don't vent that attic, any residual heat escaping from the living space warms up the underside of the roof deck.
Okay.
So the snow sitting on top of the shingles begins to melt, even when it's freezing outside.
Right, and water runs downhill.
Exactly. The water runs down the roof until it hits the eaves, the overhangs. Now, the eaves don't have the warm house underneath them, so they remain freezing cold.
Oh, I see where this is going.
That liquid water instantly freezes, creating a massive block of ice called an ice dam.
I've heard horror stories about ice dams.
They are awful. As more water runs down, it pools behind the ice dam, backs up underneath the shingles, and leaks straight down into your walls and ceilings.
Ah, so the thick insulation on the attic floor keeps the house warm, but the cold outside air flowing through those vents keeps the roof cold so the snow doesn't melt unnaturally in the first place.
You got it. And it also acts as a crucial drying mechanism. Any water vapor from, cooking or showering that manages to diffuse through your ceiling gets swept away by that ventilation channel before it can condense on the cold wood framing and cause mold.
That is brilliant. It completely flicks my understanding of how an attic functions. But what if your architecture doesn't allow for that? What if you have a vaulted ceiling or a finished cathedral ceiling where there is no flat attic floor?
Well, that geometry forces you into an unvented assembly. Since there's no attic floor to lay material on, the insulation has to move all the way up, directly against the underside of the roof deck.
So the attic space becomes part of the house.
Exactly. Empty space above your drywall becomes part of the conditioned home. It is inside the thermal envelope.
And this is where that hybrid technique they called flash and bat comes into play.
Yes. It's a fantastic compromise between high performance and strict budgets. First, a professional applies the flash. which is a layer of closed-cell spray foam directly onto the underside of the roof sheathing.
We'll get deeper into spray foam in a minute, but I know closed cell is incredibly expensive.
It is. So instead of filling the entire 10 to 12-inch rafter cavity with this liquid gold, they stop at a couple of inches, just enough to create a barrier.
So what's the primary goal of just that thin layer?
Condensation control. It prevents warm, moist indoor air from ever touching the freezing cold roof deck. In a cold climate like Zone 5, building science dictates that foam layer needs to provide at least 41% of the total R value of the roof assembly.
Why 41%?
To keep the dew point within the foam itself, not on the wood. Once that airtight vapor impermeable layer is cured, the installers fill the rest of the cavity with cheaper fiberglass or mineral wool. That's the bat.
Flash and bat, that makes total sense, which perfectly segues into the material choices. We know where the material is going, but what are we actually putting up there?
Right, the menu of options.
Before we break down the menu, let's establish a baseline, because we keep throwing around the term R value. What does the R actually stand for?
R stands for resistance, specifically resistance to conductive heat flow. So the higher the R value, the better the material is at slowing down the transfer of heat from a warm space to a cold space.
Got it. Higher number is better. So let's start with the classic. The pink fiberglass bats and blown-in fiberglass. It's undeniably cheap, right?
Very cheap. The cost data suggests about $1.50 to $2.50 per square foot installed.
But here's a detail that genuinely surprised me. If you take a thick R19 fiberglass bat and try to cram it into a smaller cavity, say a really tight rafter space, it actually loses its insulating power.
Yeah, people do this all the time. They think they're somehow packing more insulation into the space for extra warmth.
Right, like packing a snowball.
Exactly. But remember the mechanism we talked about earlier. Fiberglass insulates by trapping microscopic pockets of still air. The glass fibers themselves actually conduct heat pretty well. So when you compress a bat, you squeeze out all those tiny air pockets. You increase the density of the glass, which creates a faster thermal bridge for the heat to escape. You are literally crushing its ability to insulate.
That is such a huge gotcha for DIYers. Plus, as we established, it offers basically zero resistance to air movement. It's essentially a very expensive wind filter if your attic isn't perfectly sealed.
Correct.
So what's the next step up?
Cellulose. This is blown-in insulation made primarily from shredded, recycled newspaper.
Okay, I have to say, shredded newspaper in a dry, hot attic sounds like the ultimate fire hazard.
It really does sound terrifying. But it's highly treated with borates, which make it extremely fire retardant and pest resistant. Mice and insects actually hate this stuff.
And structurally, it behaves differently than fiberglass bats, right?
Yeah, because it's blown in as a loose fill material. It settles like a dense, heavy snow. It wraps perfectly around every single pipe, wire, electrical box, and awkward nook and cranny.
So it fills the gaps better.
It creates a seamless blanket. And because it's much denser than fiberglass, it actually slows down air movement quite a bit. It doesn't replace the need for air sealing, obviously, but it acts as a really good secondary buffer.
And what's the cost like?
At around $2.50 to $3.50 a square foot, blowing a thick layer of cellulose over a flat attic floor is often the absolute sweet spot for older homes.
Which brings us to the heavy hitter of the insulation world, the material that completely changes the rules of building science. Closed-cell spray foam.
Oh, it really is a modern marvel of material science.
Let's break down exactly how it works, because it's not just a sponge. It has an incredible R value of 6 to 7 per inch, right? But more importantly, it acts as an insulator, an air barrier, and a vapor barrier simultaneously. And I read that if you spray it on the underside of a roof deck, it practically glues the building together.
It does. It adds immense structural racking strength to the roof against wind and snow loads.
That's crazy. How does it do all that?
The secret is in its microscopic structure. Unlike fiberglass or open-cell foam, closed-cell foam is made of millions of tiny, rigid, completely enclosed plastic bubbles filled with an insulating gas.
Okay.
Because these bubbles are closed off from one another, water molecules physically cannot pass through, air cannot pass through. It creates an impermeable, monolithic seal.
That sounds like the ultimate solution. Honestly, why wouldn't everyone just use this everywhere?
Well, cost.
Right. Common sense has to kick in. The data shows the stuff costs $5 to over $7 per square foot.
Exactly.
So if I have a standard, flat, empty attic, spraying the entire attic floor with closed cell foam seems like massive overkill.
It is usually massive overkill, and honestly, a poor allocation of your budget.
Hmm.
If you have a flat vented attic, your best return on investment is a meticulous surgical air sealing job with canned foam around all the edges and penetrations, followed by blowing 15 or 18 inches of cheap cellulose right on top.
So you get incredible performance for a fraction of the price.
Exactly. You reserve the expensive closed-cell spray foam for places where space is at a premium and moisture control is critical, like those unvented cathedral ceilings we discussed, or finished attic walls.
It's a game of strategy. Put the expensive stuff only where the physics demand it.
Match the material to the mechanism.
Now, at this point, you might be feeling pretty motivated. You've got the strategy, you understand the materials, you might be ready to rent a blower machine and spend your weekend in the attic.
But hold on.
Yes, hold on. Because insulating incorrectly isn't just a matter of energy inefficiency, it can be incredibly dangerous. We have to talk about the danger zones lurking in older homes.
Attics are time capsules, and some of the things buried up there can literally burn your house down or cause severe respiratory disease if you disturb them.
Let's tackle the fire hazards first. Recessed lights, the ones embedded right into your drywall ceiling.
Very common.
Older, non-rated recessed lights generate a tremendous amount of heat from those incandescent bulbs, and they were originally designed to sit in an empty attic with open air around them to dissipate that thermal energy.
Right. Think of them like a toaster. If you take a hot toaster and bury it in a thick blanket of cellulose or fiberglass, that heat has nowhere to go.
Oh, man.
It builds up rapidly until it hits the ignition temperature of the surrounding materials. It's actually a very common cause of attic fires.
That is terrifying. So what do you look for?
If a recessed light is going to be buried in insulation, it must be explicitly labeled as IC rated. That stands for insulation contact.
IC rated. Got it.
The housing of an IC rated fixture is designed to stay cool even when completely smothered. If you have older fixtures, you either have to build specialized airtight fire-rated boxes over them for insulating, or, much better, just swap them out entirely for modern, cool-running IC-rated LED fixtures.
Okay, another hidden fire hazard we saw. Knob and tube wiring. If your home was built before 1940, you might still have active knob and tube electrical circuits running across your attic joists.
And just like those old lights, knob and tube wiring relies heavily on open-air circulation to dissipate the heat generated by the electrical current.
So burying them is bad.
Very bad. The National Electric Code strictly forbids packing insulation around active knob and tube. Trapping that heat is a severe code violation and a massive fire risk. You really have to hire a licensed electrician to decommission and replace those circuits before you add a single inch of insulation.
Okay, so fire hazards are bad, but the health hazards are arguably scarier. We need to talk about vermiculite. I had never even heard of this material before diving into these building science manuals.
Vermiculite was wildly popular as an attic insulation for decades, especially from the 1920s all the way through the 1980s. Visually, it looks like loose, pea-sized, flaky gravel. It has a gray, brown, or silvery gold color.
And the material itself, vermiculite, isn't inherently dangerous, right? It's just a naturally occurring mineral.
The problem isn't the vermiculite. It's where it came from. A massive percentage of the vermiculite sold in the United States during the 20th century was mined from a specific facility in Libby, Montana.
And what was wrong with that mine?
Geologically, that vermiculite deposit was situated right next to a massive deposit of naturally occurring asbestos.
Oh, no.
Yeah, so the vermiculite became heavily cross-contaminated during the mining process.
And asbestos fibers, when they become airborne and inhaled, are highly carcinogenic. They cause mesothelioma and other severe lung diseases.
Exactly, which is why the rule is incredibly simple. Yeah. If you look in your attic and see something resembling flaky gray gravel, do not touch it. Do not disturb it. Do not try to sweep it up or vacuum it.
Just assume it contains asbestos.
Yes. Assume it contains asbestos. You have to hire a certified professional to take a sample for laboratory testing before you can do any work up there.
Okay. Do not touch the gray gravel. Got it. But let's say your attic is completely clear of asbestos, clear of old wiring, and hot lights. There is still one major building science danger zone that can completely rot your roof from the inside out. The moisture trap.
Ah, yes. The dreaded double vapor barrier. This is where well-meaning DIYers just destroy their homes.
Let's explain what that is. A vapor barrier is exactly what it sounds like, a material that stops moisture vapor from moving through a wall or ceiling. Heavy polyethylene plastic sheeting is a Class I vapor barrier. foil-faced foam board is a vapor barrier.
Right. And the golden rule of building science is that any wall or ceiling assembly must always have at least one direction to dry out.
Because water always finds a way in, doesn't it?
Always, whether it's a microscopic roof leak, condensation from a sudden temperature drop, or just high indoor humidity from taking a long, hot shower, moisture will eventually enter that ceiling cavity.
So picture this scenario. A homeowner staples heavy plastic sheeting on the warm inside of their ceiling, right behind the drywall, to stop drafts. Then they go up to the attic and put a layer of foil-faced insulation board on the cold exterior side of the joists to add R value.
Yeah, boy.
They have just sandwiched their wooden ceiling joists between two totally impermeable layers. They essentially built a giant plastic bag.
And the moment moisture gets inside that bag, it's trapped. It hits the cold outer barrier, drops below the dew point, and condenses into liquid water.
And it can't escape.
Because there's plastic on the bottom and foil on the top, that water has absolutely nowhere to evaporate. It just sits in the dark, soaking into the wood framing. It turns the entire ceiling cavity into a massive mold incubator.
That is a nightmare.
The wood rots, the drywall turns black and crumbles, and the structural integrity of the roof just fails. You must ensure your vapor control strategy allows the building materials to breathe and dry out, which is usually toward the interior in a cold climate.
Wow. So what does this all mean for you, the homeowner? Insulating your ceiling is clearly not just unrolling some pink fluff and calling it a weekend. It's a comprehensive game of strategy.
It really is.
You have to understand your home as a holistic system. You must seal the air leaks first, or your insulation is largely useless. You have to tailor your material choices to the specific physics of your roof architecture, and you have to rigorously respect the hidden hazards up there.
And it's a strategy that is rapidly becoming mandatory. As we look at state energy codes, places like Connecticut in Climate Zone 5A are pushing toward an R60 prescriptive code requirement for ceilings.
R60, that is huge.
Achieving R60 requires a massive amount of highly performing, perfectly installed thermal resistance. It highlights just how critical the ceiling boundary is to the long-term survival and energy efficiency of a modern home.
It really does. But before we wrap up today's deep dive, I want to leave everyone with a thought to mull over. You brought this up when we were reviewing the evolution of these strict building codes before we started recording, and it really stuck with me.
Oh, about the paradox.
Yes. The ultimate paradox of modern green building. As our building codes push us harder and harder to create these highly insulated, perfectly airtight environments, essentially turning our houses into giant, sealed thermoscottles, what happens to the natural breathing that older homes relied on for a century?
Exactly. I mean, think about the drafty 100-year-old farmhouse that never had a mold problem simply because the winter wind blew right through the walls and dried everything out.
By eliminating every single natural draft in the pursuit of absolute energy efficiency, are we inevitably moving toward a future where every home, no matter how small, requires complex mechanical lungs just to survive?
Mechanical lungs, like energy recovery ventilation systems, ERVs. We are sealing these houses so tightly that the indoor air rapidly becomes toxic with our own carbon dioxide, cooking fumes, off-gassing furniture, and shower humidity.
So the house will literally suffocate unless a machine actively breathes for it.
Basically, yeah. We build a perfectly sticky box, and then we have to deliberately cut a hole in it and install a computerized fan just to give ourselves fresh air.
It forces you to look at a house as a living, breathing organism rather than just a static box of wood and drywall. And the ceiling is its most vulnerable membrane.
It's an ecosystem. Change one variable, and you alter the whole environment.
That is a perfect place to leave it. Thank you for joining us on this deep dive into your home's thermal envelope. Our challenge to you this weekend: grab a good, bright flashlight, pop open that attic hatch, and take a look at what is really going on above your head. Check if your house's winter coat is actually zipped up, or if you've been leaving the zipper open this whole time. Stay curious, and we will catch you on the next deep dive.